Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone back to ITDR2103 Discrete Mathematics. In this session, we will discuss about the topic of lecture 10, which is graph theory. Now, graph theory consider like a different topic in discrete mathematics, which is you didn't come before earlier, where we need to learn about the lingo and the jargon. So in today's session, as it is the introductory session, we will introduce what do we mean by a graph. We'll introduce the vertices, edges, incidence function, and then we will have a look on the degree vertices sequence, types of graphs, walks, path, and cycle. So this session is going to be a bunch of definitions and terms. All right. Now let's start with the definition of a graph. A graph is triple, where we got three main things. V is a finite non-empty set called the set of vertices. E is a finite set called the set of edges. G is a function called the incidence function that assigns to each edge a one-element subset V or a two-element subset V and a W, where V and a W are vertices. Now, this summarizes the concept that the graph is a number or a collection of vertices and edges. Let's see the example here. In case I got this graph with those vertices, we can label the vertices with the names. So here we can have it like V1, V2, V3, and V4. Now those vertices are connecting to each other through edges. So here we have E1, E2, E3, and here we got E4 and E5. All right. Now, if we want to express the following graph, we can use the triple here. So we can say that this graph consists of vertices, edges, and incidence function. Vertices of this graph are V1, V2, V3, V4. Edges in this graph are E1, E2, E3, E4, and E5. And we came to the incidence function. The incidence function should show which edge is connecting which vertices. For example, if we go to edge 1, so G of edge 1 is equal to, edge 1 is connecting the two vertices or the endpoint vertices, which are V1 and V2. E2 is connecting between V2 and V3. G of E3 is connecting between V1 and V3. And finally, it's not finally, we do have E4 and E5. E4 is connecting between V4 and V2. And finally, E5 is connecting between V4 and V4. And if you notice here, if we go back to the definition of G as a function, it says that assign to each edge a one-element subset or a two-element subset. So all the edges in this graph are connecting between two vertices, except E5, which is connect between one vertices. So start from E4, V4, and it is back to V4. All right. Another way we use to express the incidence function is using the incidence table. An incidence table, all what we need is we need to first express our edges. Here we got E1, E2, E3, E4, and E5. And we need to show what are the end vertices that connecting those edges. So here we got the end vertices. For E1, it is connecting between V1 and V2. E2 is connecting V2, V3. E3 is connecting V1, V3. E4 is connecting V4, V2, and E5 is connecting only V4 to V4. And here we got the incidence function in an alternative way, which is the incidence table. Okay. So let's consider we have this graph here. We will introduce some terminologies on this graph. So to start with, let's first identify our graph here. So the following graph consists of vertices, edges, and G function. The vertices in this graph are V1, V2, 3, 4, 5, 6, and V7. The edges are E1, E2, 3, 4, 5, 6, and E7. And for the following graph, since it's quite big, let's just straightforward create the incidence table, and we will have it in here. So here we got the incidence table. And as we mentioned before, the incidence table shows which edges is connecting which end vertices. All right. Okay, I'll have a line, try to be straight. And here we got 7 edges. So here 1, 2, 3, 4, 5, 6, and 7. Now, if we can see that E1 is connecting V1 and V2. E2 is again connecting V1 and V2. E3 is connecting V3, V4. E4 is connecting V3 and V6. E5 is connecting between V2, V4. E6 is connecting between V3, V6, and E7 also connecting between V3 and V6. So here we just write the definition of the following graph. Now from here, we can introduce some terminologies. If you notice that E1 and E2 are having the same endpoint. So E1 is connecting V1 and V2, and E2 is connecting V1 and V2. Also, E6 and E7, they are connecting the same endpoint. Now, what do we call these? E1 and E2, E6 and E7 are called as parallel edges, since they are having the same endpoint. Also here, we got E6 and E7 as a parallel edges. Also, E4 is connecting the same endpoint. So here we got 3 parallel edges. All right. Another thing is, if you notice here in the same graph, we got V5 and V7 with no edges. So we call those vertices as isolated vertices when they are sitting by themselves. All right, so we knew that H2 points with an edge called an endpoint, H2 edges that have the same endpoint called as parallel edge, and those are with no edges called as isolated vertices. All right, now we have something called the first adjacent vertex. Adjacent vertex is when we got an edge connecting it. So we can see here that V1 and V2 are adjacent matrix, or we can say that, vertex, or we can say that V1 is adjacency to V2. Here we got V4 is adjacent to V2 and V3, which means that there is an edge connecting those vertices, and we can apply this concept to the whole graph in here. All right, incidence vertex is when we got like two vertices, two endpoints with the same edge. Okay, all right. Something else need to be discussed here is the degree of vertex and sequence degree. Now, degree of a vertex is basically the number of edges assigned to a vertex. For example, V1, or we usually write it as D V1, for example, or degree V1. So the degree of V1 is, V1 has 2 edges, so it's equal to 2. Degree of V2 is equal to 1, 2, and 3. Degree of V3 is equal to 1, 2, 3, 4. So here we are calculating the number of edges assigned to a certain vertex. Now, the degree vertex can be even, and we call them as even degree vertex, or it can be an odd, and we can see that it is odd degree of a vertex. Right, now let's check this example here just to make sure that you are familiar with the terminologies. Consider the graph given below. First thing we need to do is, let's just define this graph. And we already says that a graph is a triple where it consists a set of vertices, set of edges, and incidence function. Now in this graph, we can see that the set of vertices are V1, V2, V3, V4. Set of edges are E1, E2, and E3. Now G, which is the incidence function, is for each edge. So here we got that for edge 1, it is connecting V1 and V2. For edge 2, it is connecting between V3 and V3. So we can write it as V3 and V3. And finally, edge 3 is connecting between V4 and V3. In this graph, we do not have a parallel edge and we do not have an isolated vertex. However, we got here something called loop, where endpoints are the same. And when I said endpoint, I mean the end vertex should be same. So if you notice here, when we write the incidence function for E2, we can see that it goes from V3 to V3. So we call this edge as a loop. All right, now let's talk about the degree vertex. Now the degree of V1, how many edges are assigned to V1? We can see that they are 1. Degree of V2 are also 1. Degree of V3 is 1 and 2 and 3. So we consider the loop as a degree of 2. So the V of V3 are 3 and degree of V4 is equal to 1. And from here we can see that all the degree vertex are odd degree. All right. Another example is here. This example, we got 2 graphs and we need to find the degree of each vertex in the graph below. So here it's basically asked for the degree, so no need to define the graph itself. So we can see here that I got 4 vertices for graph A. V1, V2, V3, V4. The degree of V1, we can see that there's only 1 edge assigned. V2, we got 1, 2. V3, we got 1, 2, 3, 4. And V4, we got 1, 2, 3, and 4. And as we mentioned before, this is a loop when we got the endpoint, the same vertex. Let's see the graph B. So here again we got 4 vertices and we need to find the degree of each vertex. V1 is 1, V2 has only one edge, V3 got 1, 2, 3, 4, since they are 2 loops, and V4 is equal to 2. From here we can see that here we got the even degree, and here we got the odd degree, and here we got 3 even degree and 1 odd degree. A new concept we can learn here is the degree sequence. A degree sequence is the same as degree vertex, however it's written in the same line. So here we got 4 vertices, so we will have 3 columns. All right, V1 has only 1, so here we got 1, V2 2, V3 4, and V4 sorry. The degree sequence for the following graph is equal to 1, 1, 4, 2. All right, so the degree sequence for a graph is putting every graph is a unique degree sequence. We can completely construct different graph having the same degree sequence. So the degree sequence is just identify each vertex, how many edges are connecting to them. Let's see this graph and we want to write the degree graph. Okay, we can start as we did here, vertex by vertex. All right, so we can say like D1, dV1, V2, and here we can see that V1 are connecting to 1, 2, 3, 4 edges. V2 are connecting to 1, 2, 3. V3 are connecting to 1, 2, 3. And V4 are connecting to 1, 2, 3, and 4. So the degree sequence for the following graph is equal to 4, 3, 3, 4. Okay? Now this graph, if we got the degree sequence, we can draw another graph with the same degree sequence. For example, if we got V1, V2, V3, V4, and here we got that there's for V1 it got 4, so if we can have it as 1, 2, 3, 4, and then V2 got 3, so 1, 2, and we need one more, so we will take it to V3. V3 got 3 degrees, so here we got 1, 2, 3, and we can have it as 1, 2, 3, and V4 should have 4, which is 1, 2, 3, and 4. So here we create a completely different graph from the same degree sequence. All right, so we can have a question like ask us to draw a graph from the degree sequence. So first thing we do is we know how many vertices we've got here. So here we can see that 1, 2, 3, 4, 5, 6, 7. So here we got 7 vertices. Let's say this is V1, V2, V3, V4, V5, V6, and V7. So from the degree sequence here, it's really obvious that V1 is isolated vertex because it has a degree of 0, which means no edge are assigned for this vertex. V2 got 3, so we can just do it like this. هذه 1, 2, and we can assign this to V5. Okay, V3 got 4, for degree of 4. So here we got 1, 2, and we can have it as 3, 4. V4 also got 4, so we can have it as 1, 2, and here we got 3 and 4. Now V5 got 5, so here 1, 2, 3, 4, 5. V6 1, 2, 3, 4, and 5. And V7 1, 2, 3, 4, and 5. So here we draw a graph. So if you try to draw a graph for the following degree sequence, you might get a completely different graph, which is absolutely also right. So from here, we can introduce our rule in a graph theory. It says that in any graph, the sum of degree sequence is equal to 2 multiplied by number of edge. Now let's check if this rule is applied in our graph here. First thing we can do is let's add the degree sequence. So here we got 0 plus 3 plus 4 and 4, 5 and 5 and 5. And we want to check, is this equals to 2 multiplied by the number of edge? So if we add those together, 4 and 4 is 8, plus 3, 11, plus 15 is 26. Now, how many edges do I have in this graph? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So 2 multiplied by 13 is equal to 26. And here we got that the relation is definitely correct. All right, let's see this question here. Here's asked to find how many vertices are there in a graph with 20 edges if each vertex is a degree of 5. Okay, now from the rule we already identified earlier, we knew that sum of degree sequence is equal to 2 times number of edges. So here we got that I've had 20 edges, so 2 times 20. And here we don't know the number of vertices, so I can identify how I will add those degree sequence together. However, here it says that every vertex in this graph is of degree 5. So we can have it like 5 multiplied by n, which is the number of vertices. Alright, now 5n should equal to 2 times 20, which is 40. Now, in order to find the value of n, we will divide by 5. And then we got that n is equal to 8 vertices. So from the rule, we can find the n, or the vertices of a graph, if they all have the same degree. All right. Now let's move the types of graph. Now basically I have two main types of graphs. We do have the undirected graph, which is the one we've already saw in this session, and we've got the directed graphs. Now let's first speak about the undirected graph, then we'll move to the directed graph. The undirected graph is whenever I have a graph with edges that do not have a direction. So if we name this as A, B, C, and D, then edge X is linked between A and D, which is also the same edge is linked between D and A. So this is undirected. The edges does not have a direction. It's only a link between two vertices. Now the undirected graph, we've got 4 types to discuss here. The first type is simple graph. In a simple graph, I do have a graph that do not contain parallel edge and do not contain a loop. Example, if we got this graph here with those edges, we can see that there are no parallel edge and no loop. So we can call this a simple graph. However, if we can see this graph here, we can see that they got a parallel edge, which is considered not a simple graph. This is the first type. The second type is regular graph, where each vertex in a graph has the same degree. For example, the following graph considered as regular graph because this vertex is a degree 2 and the following vertex is a degree 2, this one also, and this is also. And we can call a regular graph by the degree and then regular graph. So you can see here that we've got 2 regular graph, which means each vertex in this graph is a degree of 2. So it has a 2 connected edges. All right. Then we got the complete graph, where each single edge in where each single vertex in the graph is connected to each other. So we call this as a connected graph or a complete graph. Now the number of edges in the connected and completed graph is basically equals to number of vertices minus 1 over 2. And here we can have the number of edge for a complete graph. The final type of the undirected graph is named as puppeted graph, where we can separate the vertices in this graph to two groups, where the part of each group is not connected to each other. For example, let's see this graph. We got a graph with 5 vertices, and we got the connection as you can see here. So if we call this as AB, C, D, and E, so if we separated those vertices to two groups, then we can have like A has a connection to C, D, and E, and B also got the connection between C, D, and E. So the elements of one group are not connected to each other. So A and B, there's no connection. C, D, and E, there's no connection. The only connection is between those two groups. The other type of graphs is the directed graph. It is something like the undirected graph. So let's suppose I got the same graph here, A, B, C, and D, and we got the same connections. However, in the directed graph, the connections should have a direction. So this edge is going out from A to B. And we got this connection that coming out from B to D. Here we got that the edge here is going from D to A, and the same will be in here. All right. Now, if we are trying to write the incidence function, where we say it's like g of x is equal to, for example, if we call this as x, now the edge x is actually going from D to A. Now, this two vertices, if we just convert as places, we will not get the same as what we get in the undirected graph. Now, changing the places of the vertices means the directions change, which means it's usually not equal to the one opposite. So in a directed graph, the edges are directed by arrow, so it comes out from a vertex to another vertex. Now from here, we can see that in a directed graph, I have a n degree and out degree. Okay, for each vertex, we have those two edge type. So either we got the n degree or the out degree. For here we got that vertex A, B, C, and D. Now if we see the vertex A, we want to check the n degree, so we will check for all the arrows that pointing to this vertex. So here we got one arrow is pointing to A and one arrow is coming out of A. All right. For B, we got two arrows are pointing in, one are pointing out. For C, one is in and one is out. And D, we got two is out, one is in. So here, 1 and 2. Now we got a theorem says that sum of n degree should equal to sum of out degree, and it is also equal to number of edges on this graph. So if we try to check out this theorem, if it's working or not, let's start counting. Now here, the n degree for this graph is equal to 1 plus 2, 3 plus 1, 4 plus 1, 5. And here we got out degree, 1 plus 1 is 2 plus 3, then 1, 3, and 2 is also 5. Now, if we count here the number of edge we got, 1, 2, 3, 4, and also we got it as 5. So this is something we really need to take care of in the directed graph. Now, let's move to the last part of our session, which is walks, path, and cycle. Starting with the more general terminology here, which is walk. Walk is basically the journey from one vertex to another vertex, moving through edges and vertices. So, okay, let U and V be two vertices in a graph G. Then a walk from U to V in a G is an alternating sequence of n plus 1 vertices and n edges of G, beginning with vertex U, called the initial vertex, and ending with vertex V, which is called the terminal vertex. Let's see the example here. We got the following graph, and we have like 8 vertices and 12 edges. Now, if we not here, we can see that moving from V1 going through this to V6, consider as a walk. And we usually write it as vertex, which edge we need to go, and then which is the next vertex. So this walk is V1 through E1, we reach V2, and through E2, we reach V3, and through E7, we got V6. So this called as a walk, moving like this. All right. Okay. Now we got that V1 is initial vertex. V6 is terminal vertex, where the walk is ending. In a walk, we can repeat edge and we can repeat the vertex. For example, going through V1 to E1, V2, E4, V8, V4, E8, V5, E5, then we go E2, then E7. We can see that here we repeated V2, and we also can call this as a walk. All right. Now we got two terminologies here, which is called the closed walk and the open walk. The closed walk, when I have the initial and terminal vertex are the same. So it's like going from V1 to V1. We have multi ways to do this. Open walk is what we got here when we have initial and terminal vertex are different. So a walk is basically the journey from one vertex to another vertex where we can repeat the vertex and repeat the edge. And we have two main walks, which is the closed walk when we are the terminal and the initial vertex are the same, and we got the open walk where we got the terminal and the initial vertex are different. Length of a walk is the total number of accuracies of edges in the walk. For example, if we got this example, the length of this walk is 3 because we got here 1, 2, 3, 3 edges, right? Moving to the second type of walks, which is a path. Now a path is basically a walk with no repeated vertices except possibly the initial and the terminal vertex. Now if you notice here the same graph, we can see that moving from V1 to V7 through E3 and E9. We call this as a path. In this path, we can see that we are moving from initial to terminal with no repeated edge or vertices. Okay? A cycle is a closed path, which is called a circuit that does not contain any repetition of vertices except the starting vertex and the terminal. And we call this as a cycle. And sometimes a cycle can have a number in before, which is the length of this cycle. Again, back to our graph, and we can see here that moving from V1 to V1 consider as a cycle. And here we can see that it will start V1 E1, then V2 E5, then V5 E8, and V4 E3, and we reach to the starting point. So we call this as a cycle. And if you notice here, we go through 4 edges, so we can say that this one is a 4 cycle, or the length of my cycle is 4. So as we see, we start with the work, which is the more general terminology, where it is a journey between one vertex to another vertex, where repetition of the vertices are allowed and repetition of edges are allowed. Now a walk is named as a trail if we repeated only the vertices with no edge repeated. A path is no repetition for either the vertices or edge except the initial and terminal vertices. Circuit is when I can repeat the vertices and no repetition of the edge, and cycle when we are not able to repeat neither the vertices or nor the edge except also for the initial and the terminal vertex. And here we reach the end of this session where we discussed about an introductory of a graph. We introduced the vertices, edges, incidence function, and then we saw the degree vertex, degree sequence, types of graphs, walk, path, and a cycle. Thank you guys for listening. We'll see you inshallah in next session.